Alright guys, so today we're going to talk about polar coordinates. So what polar coordinates are going to be based on is a very simple idea. And that is that if you were to consider your unit circle, not quite a circle, but let's say that's the unit circle, for every angle theta, you have a point in the unit circle. So if you have a point in the plane, you can always associate that point with the angle that it corresponds to and with a radius. So if you have a point with coordinates x, y, let's say there, excuse me, then x, you can think about x being given by the radius, which is going to be the distance from the origin all the way out to the point, times the cosine of the angle. You've done that before. And then we have that y would be r sine of the angle. So if I give you a point that I know the radius and the angle, you can calculate the x, y coordinates just by plugging into these equations. Similarly, if you had x and y, you can always find your radius by remembering that the square of the hypotenuse is equal to the sum of the square of the sides of the triangle. And that will give you a way to find the radius. Now, you're going to have that the tangent of the angle also satisfies, satisfies y over x. I don't know if that got cut off there. It's a little bit too close to the bottom. But the tangent is going to be the y over x. But now, that, you know that equation has a lot of solutions, infinitely many, because the tangent is pi periodic. However, if I restrict my angle to be given between 0 and 2 pi, then my radius would always be positive. So I'm going to restrict that. I'm going to say that radius will be positive and the angle theta will be between 0 and 2 pi. So let's say it belongs to the interval. Let's make 0 inclusive 2 pi. Let's leave it open because 2 pi is the same in terms of angles, is the same as my angle 0 because you return all the way back. All right, so that's how we're going to use, or what the formulas we're going to be using. So for example, if I give you a point, let's say in rectangular form, let's say I give you 2, 2, for example, and I ask you to find the polar coordinates, then you would use this formula right here. And you would say, well, the radius is going to be the square root, of 2 squared plus 2 squared, which is going to be the square root of 4 plus 4, 8, which you can write square root of 8, you can write as 2 square root of 2. That would be your radius. And then your angle, you would have to find that the tangent of 2 over 2 is 1. So the arctangent, I should have written more than that. Let's start with writing the tangent. There you go, fixed it. Tangent of the angle is going to be 2 over 2. This marker starts to squeak. Is equal to 1. So the angle, I can pick that to be pi over 4. Now, of course, as I said, you could do pi over 4, but then you could do pi over 4 plus 2 pi, and so forth and so on. But we want our angle to be between 0 and 2 pi, and our radius to be positive. So our radius, so this is going to correspond to the point in polar coordinates, 2 square root of 2, which is going to be my radius, and my angle, which is going to be pi over 4. I want to keep these formulas here, so I'm going to do a few examples, but every time I'm going to erase this and I'm going to keep this in view. All right, so let's do that. So let's take a look at what happens now with a point with a little bit more interesting, situation. Because what happens, think about when we take an arctangent. I didn't mention this, but the arctangent is going to spit out values. So when you put an arctangent on your calculator, it's going to spit out values between 0 and negative pi over 2 and pi over 2. Let's put a point here on the other two quadrants. Let's put it in for example, negative, let's do a 1 comma square root of 3. Something like that. A point that will still be in the unit circle, or a multiple of a point on the unit circle, so we can still compute it somewhat easily for the angle, but that is going to be outside of what we normally would consider for the arctangent. All right, so at this point, what is going to happen is you're going to compute your radius, and the radius squared is going to be negative 1 squared plus the square root of 3 squared, which that's going to be 1 plus 3, which is 4. So your radius, you're going to pick it to be 2. But now, you got to be very careful here, because the temptation would be to say, well, theta is just the arctangent. Sorry about the noise. Square root of 3 over negative 1. So negative square root of 3. Now, if you plug that in your calculator, that's going to spit the angle that corresponds to this angle here, negative pi over 3. That's what that's going to give you. But that's not the point where you're at. If you think about where you're at, it's negative 1 and square root of 3 somewhere out in this direction. Well, I did angle 1, but let's say it's in this quadrant, in the second quadrant. So you got to be very careful. What you're going to have to do is grab that angle that you got from your calculator, the negative pi over 3, and you're going to add pi. Now, if you go to your unit circle, you look at this directly, it's going to be the angle 2 pi over 3. But the arctangent really would give you negative pi over 3. That's not the angle you want, because the angle you want is this one right here. So this wouldn't be right. Theta is not going to be the arctangent, but it's going to be the arctangent plus pi on both, which is going to be 2 pi over 3. This one is one that you could see directly by doing your unit circle. However, I do want to warn you, whenever the point you're going to convert points, plot them so that you see if you land in your second and fourth quadrants, third quadrant, you will have to change your angle by adding pi. If you're in the first and fourth, I apparently don't know how to count. First and fourth quadrants, you'll have no problem. You just do your arctangent and you're fine. Why am I mentioning that? Well, because often you will not have points that are in the unit circle. So for example, if I give you something like, let's do negative 3 and negative 4, then you'd have to do your angle by doing an arctangent. So you got to be very careful with that. Let me do that one actually as an example, and then we're going to move on to computing the rectangular coordinates given the polar. Those are way easy because you just plug it here. There's not as much nuance. But let's do the angle or the point negative 3, negative 4. All right, so as I said, negative 3, negative 4. Let's convert that into polar coordinates. So our radius, the radius squared is going to be the sum of the squares, x squared plus y squared. I don't know why I'm writing it, because we just have to plug it in. Negative 3 squared plus negative 4 squared. The negatives cancel with the squares and you get 9 plus 16, which is going to be 25, from where you're going to get that your radius is 5. All right, so now this is where you got to be careful, because it's going to be a little tricky, because your angle is going to be here again in the third quadrant. But notice that when you do the tangent of the angle will have to be negative 4 over negative 3. So this is not in the unit circle, so you would do your arctangent. Why did I do that? I'm not going to fit it there. But it's going to be the arctangent of 4/3. Now, be very careful, because that's going to give you an angle between 0 and pi over 2. Because remember, the arctangent is the inverse function of the tangent, but just the restriction of the tangent between negative pi over 2 and pi over 2, that's the restriction we make, so that the function is 1 to 1. Therefore, the inverse is well defined, and it's a function. So when you put in your calculator, that's going to give you an angle over here. If you just write down carelessly the arctangent of 4 pi over 3, you're going to get it wrong, because it's going to give you this angle, you gotta add pi to it because you're in the because you're going to be in the third quadrant in this case. So again, if you're in the second or third quadrants, remember to add your pi and you'll be all right. If you're in the first and fourth, nothing to do because you're going to get the right angles, not right angle as in triangle, but in the correct angle from taking the arctangent. All right, so let's do one just from polar to rectangular. So let's say you have a radius of 3 and an angle of pi over 3. This one, there's really no mystery. You're going to plug it into your formula. X is going to be 3, which is the radius times the cosine of pi over 3. And y is going to be 3 times the sine of pi over 3. So the point that is going to correspond is going to be the cosine of pi over 3 is going to be 1/2. So it's going to be 3/2. And the sine of pi over 3 is square root of 3 over 2, which is going to be 3, then root of 3 over 2. So that's how you get your point in rectangular coordinates from polar. That's very straightforward. Let's go ahead and plot one graph here real quick. All right, so let's plot a quick graph here. So to do that, just as with parametric equations, you're going to have to make a table. So I did it backwards. Theta, and then you get the radius. It's okay. So start with 0, angle 0. You're going to have that cosine of 0 is 1. Let's go to pi over 6. Cosine of pi over 6 is going to be square root of 3 over 2. Let's do to pi over 4. Cosine of pi over 4 is square root of 2 over 2. And then I'm going to go to pi over 3. I'm going to do just angles around that I know from the unit circle. So cosine of pi over 3, 1/2. And if I plug pi over 2, that's my whole first quadrant, the angles I know from the unit circle. That's going to be 0. Let's plot those real quick and see what we get. So you draw your quadrants as you would, but this is what you do now. You're going to draw the angles. Angle 0, there. Angle pi over 6, pi over 4, your angle pi over 3, and pi over 2. And now we're going to measure. When the angle is 0, radius is 1. So I'm going to be out here. Let's say this is 1. There. When the angle is pi over 6, I'm going to be at square root of 3 over 2. So a little bit smaller than 1, but not too much smaller. Then at pi over 4 is root of 2 over 2, somewhere there. At pi over 3 is going to be 1/2. So if this is 1, 1/2 is roughly here. And then at pi over 2, I go down to 0. So I get that in my first quadrant. So that curve looks like this first half. That. All right, so now I'm going to look at, I got to continue my table, but I don't have space, so I'm just going to do the angles and we're going to see what we get. So we're going to do 2 pi over 3. Then I'm going to do 5 pi over 4. And then 5 pi over 6. Let's write them out. 2 pi over 3. 5 pi over 4. Doesn't look like a 5. Then this is going to be a... Alright, and now this would be just my next point, which is going to be pi. Alright. Yeah, I moved it, this rotated a little bit. Nonetheless, if I plug 2 pi over 3, the cosine of 2 pi over 3, remember, is going to be negative 1/2. So instead of going here, what's going to happen is the negative measurement of the radius is going to send me to this side. So it's going to be negative 1/2. So it's going to be roughly is going to be just a reflection of this point, really. So it should be that. And then if you go to 5 pi over 4, cosine of 5 pi over 4 is going to be negative square root of 2 over 2. So it's going to be sending me in this same direction of 5 pi over 4, the bisecting angle. But it's going to send me to negative root of 2 over 2. So I'm going to be basically reflecting this point. And then the next one, I'm going to be reflecting that point. And what I'm going to end up with, if I plot all the points, is technically this would be a circle. So that is how you would do your graphs. So we're going to look at the graph of the function r equals sine of 2 theta. All right, so what I'm going to do, I'm going to do a table, and I'm going to draw the graph. I'm going to do my best to draw the graph here. And the way you're going to draw your polar coordinates is in the following way. You're going to pick some angles. Let's do pi over 3, pi over 4, and 2 pi over 3. Of course, 0 and pi over 2 are also very, very useful. And I'm going to continue like that. So 2 pi over 3 here. So I'm going to grab those rays. And I'm going to make a little table here where I'm going to plug the angle and get the function r. I'm going to do a few of them. So I'm going to start with 0. 0, not theta. 0. Whenever the angle is 0, sine of 0 is 0. So the graph starts angle 0, radius is 0. So you're starting the radius you're measuring from the origin. So the graph starts there. Now I'm going to do up to pi over 3. When I put pi over 3, pi over 6, I was already evaluating. Let me just smudge it a little bit. Not the end of the world. Pi over 6, when I plug it in here, I get pi over 3. The sine of pi over 3 is going to be 1/2. Sine of pi over 3 is going to be 1/2. So I'm going to say, I'm going to go on this pi over 6 angle, and I'm going to measure 1/2. I'm going to say this is 1/2. We're going to be measuring very, very precisely, huh? Now I'm going to go to pi over 4. At pi over 4, I evaluate here, and whenever I evaluate sine of pi over 4, I'm going to end up with sine of 2 times pi over 4 is going to be sine of pi over 2, that's 1. So this is going to measure 1, so I'm going to go here 1/2 plus 1, I'm going to go out to here. So you see, the measurement I grabbed here, that's 1/2 distance from the origin on that angle. Now I'm going to grab 1/2 plus another half, so roughly I'm going to end up there. I understand that it's very iffy, but well, that's how you're going to do it. So pi over 3, when you plug it in here, it's going to be sine of 2 pi over 3. The sine of 2 pi over 3 is still going to be, wait, what did I say before? I said sine of pi over 3. I put 1/2. It was really square root of 3 over 2. Oh, fail. I mean, the sine of pi over 6 is 1/2. The sine of pi over 3, which was what I'm evaluating, was square root of 3 over 2. Thank goodness we had symmetry and we could check that. So really it wasn't 1/2, it was going to be, oh, fail. So that's going to be a little bit higher, so it's going to be there. There. And now the next one is going to be basically there. And when I go down to, oh, I feel so bad. It's not enough to re-record, but almost. When I do pi over 2, I get sine of 2 times pi over 2, which is sine of pi, which is going to give me 0. So you see, I went out here and I returned here. So if I draw that, it's going to be what is called a petal. And that's my first quadrant. Now, if you continue to graph all around, what happens with this one is actually going to be 4 petals like this. It should be very symmetric. Yeah, just like I did. Anyway, so that's going to give us the graph. So you're going to have to continue and draw your And if you look online, you're going to have the graphing paper that has all these angles already drawn for you. Oh, this one should intersect at some point, I suppose. So you may want to print those to make your graphing a lot easier. Okay, so you're going to get all those angles and then you're going to plot them and you're going to be measuring. Maybe having a ruler handy, not just my fingers like I did, would be useful, except of course if I did 1/2 versus square root of 3/2, makes a big difference. The 1/2 would have happened at pi 12's angle. Anyways, but that is how you're going to draw your graphs.